And yet another form of stronger form of relationship between classes. Let me just get rid of this composition. Is also this filled rhombus version. In this case, it's very typical in having parts in C++ program. So in this case, the filled rhombus is called composition, is the strongest form of relationship other than inheritance, where you basically say that the lifespan of insurance policy is the same as the savings account. It means that if you create savings account, it means that you instantly create an insurance policy. If you get rid of the savings account, you're also getting rid of the insurance policy class. Their life cycles are the same. They are created together and they die together. They go away out of scope together, right? Because that's the requirement, and this is by design. By the way, very simple and very straightforward type of thing to happen in C++. In Java, most likely what you're going to be getting is let me restart my clock here. What you're going to be getting is most likely a composition, which is this. A composition means that the objects can be created at different times, but when it's time to use them, most likely, the software would be expecting that both of them exist. Both of them will exist by the time they're going to be used. So that's what just the aggregation says. But the aggregation relationship, which is a weaker form of composition, basically says it's okay to create an insurance policy and 5 minutes later create a savings account, make sure that savings account has a reference to the insurance policy, and try to do some work with the savings account. That's okay. Whereas again, with this filled rhombus, the strong composition relationship, it means that as soon as you create savings account, you're also creating an insurance policy class. So that is just something that is part of this, the possibilities that you can express with those designs. Yet again, if you have savings account inheriting from the account, that's a form of composition through inheritance, right? Because there, it's absolutely given that when you have hierarchies of objects and you create those, classes, when you create subclasses, they do contain instances of their superclasses physically in their space, because that's why we can say that savings account, which is this big box, is also an account, which is the smaller box. And before, we also had account deriving from an insurance policy, and that way we also had even smaller box encapsulated inside. But that's again because you can have those multiple levels of inheritance. So these are some of the subjects that we've been discussing and trying to kind of reflect on different aspects of it, and our thinking should be shaped based on those possibilities. Sometimes composition is more appropriate. Sometimes inheritance is just very natural way of doing things. Abstract class, of course, is a class, if you recall, just once again, a reminder that abstract class is a class that declares at least one method which has no definition. It's just a declaration with a semicolon at the end. It's called abstract method in Java. It's called virtual member function in C++. It's the same thing. And what happens there is that because the method is missing, its signature is given, its interface signature is there, but the implementation of the method is not given. It makes the method abstract. It just makes it a promise. And in that case, you have to derive a subclass from the abstract class and make sure that you implement that method. That's the idea of an abstract class. And this is where C++ stops, and it says, okay, you can have abstract classes and you can have concrete classes. Concrete classes implement all of their methods or member functions, as a C++ programmer would refer to methods. Whereas in Java, you have abstract classes and concrete classes. But in Java, you can also have an interface. Interface is simply an abstract class that is made up only of abstract methods. So we talked about that, and we went through some code examples of this. And so why interfaces are useful? Both abstract classes, but specifically why interfaces are useful is that interfaces are useful in situations when you can, for example, create a particular kind of collection, such as an array list or linked list, for example, but then use the list interface, because beyond the point of creation, there's absolutely no need to be concerned what kind of list this is. Is this an array list or linked list? What kind of, what kind of container you created? You want to use an interface which is a list. At some point you did make a decision to create an array list or different kind of list. That was the decision a while ago. You made the decision. Beyond that point, the interface for array list and linked list is exactly the same. Therefore, you don't have to even remember what kind of list you've created. You don't want to be concerned about it at all. So that's why there will be a list interface, and both array list and linked list, as an example of these two collections, both will be implementing the list interface. So interfaces are very useful in terms of it's very easy to build system from separate components, right? So if you consider list to be a component of your system, then you can have array list component or double or linked list component, and both can be plugged into your application simply because beyond the point of creation you use the same uniform interface named list to talk to these objects. So they will both equally respond to methods, to messages sent to them in the same exact way, because they were designed with the same exact interface in mind, right? So that's why interfaces make it easier to make systems out of replaceable components. Tomorrow I can write brand new class named double linked list, or I could do like a circular linked list. And if I support the same interface named list, well, guess what? I can replace my array list by this doubly linked list tomorrow, like I said, and the rest of the system will not even know about any changes. You'll just recompile it, and the rest of the code, as long as the list interface is in place and we have an object which properly responds to the list interface calls, everything will work. So interfaces tremendously simplify building systems out of individual components. So that's the case. Anytime you're using interfaces, the challenge which comes with interfaces, perhaps if we want to say what are perhaps the downside of interfaces. Well, the downside is that sometimes if you use a lot of interfaces in your program, and so you create, making decision which objects to create to satisfy, that particular interface becomes somewhat a challenge, because you have more flexibility now, right? If we didn't have interfaces but instead only had concrete classes, like the only way to approach your design is like, if you need a driver license, you cannot have interfaces. You have to create the driver license class, and that's the only choice. Then the decision about what object to create is somewhat simpler, because you have only one choice. But if you have all of these objects which implement the same interface, suddenly have a lot of choices. And when you have that flexibility, your application needs to manage creation of objects. And there are different design patterns, for example, like object factories, which are components or classes in the system solely responsible for creation of objects. And so it becomes another layer in your application which you need to support, maintain, make sure they all do the right thing, and so forth. So these kind of things are related to interfaces and abstract classes. So abstract class is somewhat in between the concrete class and an interface, because it may have the data, it may have some implementation methods in it, but it has some abstract methods which are just declared but not completely written. You still need to have a concrete class that finishes the work, right? So that's why we basically discuss interfaces and abstract classes in one connected kind of presentation. Again, I'm not going too deep into these presentations, but showing you what is available in terms of these are all design decisions of that you can make. Finally, we today officially, this will be perhaps the set of topics to use would be generalization, aggregation, association, and cardinality. The commonality or something that puts these things together is that these are all forms of relationship between classes, right? And we specifically talked about aggregation. Aggregation is somewhat stronger than simple association, right? And we also discussed composition, and we will see some examples of the cardinality. But generalization is certainly also yet another inheritance relationship, or generalization relationship, as UML likes to name it. Is definitely a strong, very, very strong form of relationship between classes. And they're all could be chosen, depends on what situation you're in, what type of design you're trying to implement. So let's save this segment and then go to the presentation and see some examples of